I heave the basketball. I know it sails in a parabola, exhibiting perfect symmetry, which is interrupted by the basket. It's funny, but it is always interrupted by the basket. Michael Jordan, former Chicago Bull. A broken symmetry breaks your heart. Abdas Salam, the world treasury of physics, astronomy, and the mathematics. Broken symmetry, shattered mirrors. Our last lecture was about symmetry. It was a little bit rough going in spot. There were some heavy-duty mathematics. There were some heavy-duty mathematics. Noether's theorem and the principle of the gauge symmetry. And today's lecture is going to also be about symmetry, about the breaking of the symmetry and what that can teach us about how the world is made, and as a guide for learning about laws of physics and our understanding. Sometimes when the going gets really abstract in a colloquium, I get a little frustrated. I go to colloquia all the time, and if it is about nuclear and particle physics, oftentimes I can kind of nod my head and follow the whole time. And especially if it's another branch of the physics or some other science, I can get completely lost in pairs of colloquia. And I want to remind you that it's okay to get lost from time to time as long as I can bring you back at some point, either in this lecture or an upcoming lecture. Oftentimes, when you get lost, it's because you're learning about some brand new topic that's a little bit abstract, and as you continue along, you will learn some principles and some ideas, so that when you go back and look at what you have heard before, and it was confusing. It all begins to tie in together. There is not always a starting place when you are learning about some complicated thing. It's just a big old mess, and you just have to jump in somewhere and begin to learn more and more of it. And then the big picture begins to appear. So having said that, I want to talk about the breaking of the symmetry today, and we are going to talk about how fast fits in with the world of particle physics. Let me start off just by reminding you of why symmetry is such a lovely principle. Not just its aesthetic appeal to us as human beings, it can serve as a simplifier. If you look at a complicated system, but it's symmetrical, then your description of the system and your understanding of it can be made easier, simplified. For example, a neutron-proton system like a nucleus is not quite as complicated as you thought. You could just call them all nucleons and work out of the theory that really only has one object in there. Where the six-fold symmetry of ice teaches you something about the shape and character of individual molecules, which might otherwise be invisible to you. And it can lead to predictions and understanding in a very deep way. For example, Noether's theorem allows you to take a symmetry and predict a conservation law, which is the practical useful, or even better yet, gauge symmetry and extraordinary abstract symmetry of the nature can lead you to predict the existence of a new particle of the new force in the world. Symmetry is a wonderful thing. Right. And alas, in the real world, many times symmetry is broken. Look at your body. Okay, it's got a left side and a right side, and it seems to be quite symmetrical. Look at your hands in particular, holding in front of you. Are they the same? In many respects, they are the same, except they are totally different. You can't put a right glove on a left hand, right? They are completely different, but they are also completely symmetrical. And then you look more carefully and you notice, I've got a scar on one hand and not on the other. My body has a heart on one side and not on the other. So there are small, subtle breakings of this symmetry and many of them are accidental. Sometimes symmetry begins and then some accident of nature breaks it. And that's a common situation and that might teach you something. By looking at a scar on my hand, you learn something about the history of my life. It can also be that you learn much deeper principles, and that's where we are headed today. Let's think again about watching games and thinking about the colors of the uniforms as a slightly stretched metaphor for thinking about symmetries. So, let's go now to an American game, soccer, and we've got two teams, and imagine that one of the teams is wearing pink, and one of the team is wearing blue, and they are a bunch of little kids, and they are playing soccer. Now, the question is there an exact symmetry between the swapping the color pink and blue? In principle, there should be. The rules of the games are exactly the symmetrical. Alright. If you look in the rulebook, it's going to tell you it doesn't matter what color you are. And if everybody on one team swiped with everybody on the other team, nothing should change. So now you watch this game, and let's suppose that after watching many games, you observe that the pink team seems to win more often, okay? That's a breaking of symmetry. It might just be a subtle breaking of symmetry, and what you might learn then is in America that little girls in the second grade mature a little bit faster than the little boys, and they tend to be more coordinated and stronger. And so the pink team may, in fact, beat the blue team more often. If they are second graders, and when you are 10th graders, maybe it's the other way around. So this is a subtle breaking of the symmetry that teaches you something about the players and maybe the culture that they live in. Right. And you could also imagine playing that game I described last lecture, where you swapped the uniforms. If you take a bunch of high school students and you swap the pink for the blue, and the game might just fall completely apart, because all the little girls are laughing at all the little boys and they can't play soccer anymore. Because in our culture, it's a little bit bizarre. Boys aren't supposed to wear pink, and so again, by looking this would be more radical breaking of the symmetry. You swap the two colors and now the whole game falls apart. It's not at all the way you expected. So physicists are often looking at the systems and looking first for symmetry. It's the easiest to find symmetry when it's exact, and it's pretty easy to find when it's almost exact. In fact, sometimes it sticks out more when it's almost exact. I think artists have really mastered this. Many paintings will have some symmetrical aspect, but they are almost never perfect, geometrical, exact. And it's that slight breaking of geometry that kind of draws in you and gets your attention. So I think many times in the physics, when we are looking at a situation where there is a slight breaking of the symmetry, we notice it. Not only does it point us towards the symmetry, but it also teaches us something. For example, I've talked about the neutrons and protons in the nucleus, and I said the laws of the strongest interaction are independent of whether you are a proton or a neutron. It's a deep symmetry of nature, that it doesn't matter which you are, but it's not exact. In fact, a nucleus with two protons is not a stable nucleus. A proton and a neutron is. It's a very subtle difference in the most cases. Swapping a neutron for a proton changes the electrical properties. Electricity is very weak compared to the strong force, so normally it doesn't have a big influence. However, it can play a role. There is another symmetry that's broken between the protons and neutrons very subtly. If they were completely symmetrical, they would weigh exactly the same, and in fact, a neutron weighs about 0.1% more than a proton. It's a tiny breaking of symmetry, and it's very interesting. Where does it come from? Well, it comes from a couple of places. It teaches us, for example, that the down quark might weigh just a little bit differently than the up quark. Because after all, a neutron is made of the two downs, and an up and the proton is made of two ups and down. So a tiny difference between the quarks would lead to tiny difference between the two objects. You can use this a small breaking of the symmetry to learn something about the quarks that build up the object, even if you can't see them directly. Alright. You can also use this breaking of symmetry to learn something about electricity. What is the role of the electricity inside of the nucleus? At first, you might say, never mind, the strong force is so strong, everything is tightly bound, who cares about electricity? But it's there, it's real. Positive charge repel, but the neutrons are not repelled because they are neutral. And again, you can learn about the constant connection between the electricity and the strong force in the nucleus by looking at the differences between the nuclei that have different numbers in protons and neutrons. So, when the symmetry is slightly broken, it's easy to find. It teaches us lots of things, and we can use both the symmetry and the breaking to learn stuff. Life gets tough when symmetry is badly broken. When the symmetry is so broken that you'll hardly even recognize that there was any symmetry there to begin with. Let me try to make this concrete with a couple of examples. The first one a little bit more metaphorical, and the second one a little bit more physical. Imagine that you're at a fancy dinner and you sit down at a very large, round table, and there is a bunch of seats, and in front of each seat there is a plate, and in between the plate is a full glass of water. Now, when you sit down, there is a glass of water on your left side, and there is a glass of water on your right side. They are between the plates, and you say, this is a perfectly symmetrical table. I am completely free to choose, left or right, to grab the glass of water. Now, there might be a social convention. I never know, so what I do is, I just wait, and sooner or later, somebody around the table is going to grab their glass, and I'm paying attention. Everybody else is doing the same things. If the first person reaches out with their left hand and takes a sip, everybody is obligated. The symmetry is broken. You no longer have a choice. Because if one person goes left and another person goes right, somewhere around the table, think about it, somebody is not going to have a glass of water. And so, this is a case where symmetry is broken. Imagine a latecomer who sits down, and now everybody at the table except for them has taken some sips. So the newcomer sits down, and they see a full glass on their left side and an empty glass on their right side. They say, this table has no symmetry whatsoever, completely broken symmetry of water glasses. And they might, if they are not so bright, they might not even be able to fathom the idea that the table began symmetrically. And they might think, well, gee, you have no choice in life. You have to drink from the left glass, because that's where the water is. This analogy is not mine. It was actually invented by Abdus Salam, who is one of the winners of the Nobel Prize for his understanding and explanation of the weak force of nature, which manifests some very serious broken symmetries. And we'll come back later and talk more about Salam's understanding of the symmetries of the forces, which are analogous to this left-right choice that you have to make at the dinner table. let me give you another example that's a little bit more physics. Why? Physics. See. Supposing that you look inside of the kitchen magnet, so a kitchen magnet is a small chunk of metal, and when you stick it to the refrigerator, it sticks. Why? What's going on? Well, physicists understand magnetism as arising from the magnetism of individual atoms. And I don't want to, go on this detour to talk about why an individual atom is itself magnetic. We need a course on the electricity and magnetism to talk about that. But let's just take for granted that an individual atom is acting like a little teeny magnet, and it's got a north pole and south pole, and it's an atom, so it can be oriented any which way. So it's like a little randomly oriented atom, a little randomly oriented magnet, and in fact, if it's warm, it's jiggling around. Yes, if it is warm, it's jiggling around. Yes. First, it's pointing north, and then it's pointing west, and then it's pointing east. Now, supposing that you have a crystal, which is a whole bunch of atoms, there are various possibilities. One is that all of the atoms are pointing every which way. Then you just have a crystal. It's not a magnet at all. Yes. But what happens if all of the atoms in the crystal are magnetized in the exact same direction? Yes. Well, magnetism adds up. If they are pointing in the opposite direction, they cancel. But if they are pointing in the same direction, they add up. And so a kitchen magnet is a material where all the little atoms, all the little mini magnets are all pointing in the same direction. Right. Okay, now let's think a little bit more about why this happens. If you have a magnet and it's warm, if you warm up your kitchen magnet, it will demagnetize because there is so much thermal energy in the air. All the atoms are pointing every which way. Now imagine cooling it down. Maybe one of the atoms will be pointing in some direction, and its neighbor will say, "Hey, magnets love to be pointing in the same direction. Compass needles love to point up with the Earth's magnetic field." That's what magnets do. They like to line up. Yes. So if one atom is pointing in some direction, its nearby neighbors, if they are close enough and if they are strongly enough in interacting, may momentarily line up. Now imagine a neighbors of the pair. So you've got two that line up, and now there is a nearby third one who says, "Hey, two of my neighbors are lining up. I definitely want to line up because now there is an even stronger local field." So it's a kind of a chain reaction. Once a couple starts to line up, then it spreads. Everybody lines up. It's like a lemmings. Once somebody does it, everybody wants to do it, and this is then the spontaneous magnetization of the magnet. And the magnetic materials are materials where the atoms are closely enough and strongly enough coupled that they can do that. Now, imagine that you are a little teeny weeny physicist and you live inside the magnet and it's magnetized, right? You are living on the refrigerator and you've spent your whole life in there, and you are trying to deduce fundamental laws of physics inside the magnet. At first, you are not too bright, and you are making observations and trying to come up with rules. And it seems like many experiments that you do point north, and it's special. For example, if you build a little compass needle, it always points in one direction, always, and it doesn't matter where you go in your universe, right? You're really small, your whole universe is inside this magnet, even if you get far away from your home, right? It's like a human being leaving Earth. If you left Earth, your compass needle would point in the random direction, but not if you live inside the magnet world. Right. North is North is special to you. And furthermore, if you take the literature's particles and you take them travel, you make beams when they are going north. They go in straight lines, but when they are going west, they go in circles. So north and west are radically different directions to you. So maybe you become religious and you say, God is to the north. And maybe you're a physicist, so you say, the universe is not symmetrical. The north direction is a special direction, and the laws of physics reflect the rule that if you are going to north, life is simple, but if you are going to west, life is complicated. And then comes along a little genius mini physicist, a little micro salam, who says, no. I believe that the world is truly symmetrical, that atoms can point any which way. It was an accident of the history that they happened to line up northwards. And really, when you describe the laws of nature, they should not care about which way is north and which way is west. It's just that our world is a broken symmetry world, right? So this metaphor implies that you live in the world that's complicated and some direction is special. It requires some insight to realize that the fundamental laws are truly symmetrical, and this little mini physicist could prove that he or she is correct by heating up the world around them. And if you heat up the world around you, then all of a sudden north is no longer special, and now the symmetry becomes manifest. It becomes obvious. Ha 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 ha!